Okay, imagine this scenario. You've got a critical piece of machinery, something absolutely colossal, like a power plant turbine, and it suddenly just grinds to a halt.
Yeah, the hum just stopped.
Exactly. And the pressure in that moment, it's intense, isn't it? Every single second it's down, you're just bleeding money, a fortune.
Astronomical cost.
And the traditional nightmare, you're looking at weeks, maybe even months of downtime. Think about it. Dismantling that behemoth.
Oh, the logistics alone.
Right. Shipping it probably halfway across the world for repair, then the whole arduous task of putting it back together. It's not just a logistical headache, it's a financial black hole.
A complete operational disaster, really.
So that brings us to the core problem we're diving into today. How on earth do you repair something like a damaged turbine casing, quickly, in short order?
It sounds almost impossible when you put it like that.
It really does. Getting a piece of equipment that size fixed precisely and quickly without moving it an inch.
Yeah.
Well, get ready for a game-changing solution that completely flips that nightmare scenario on its head.
And that solution is on-site portable line boring.
Exactly.
That's right. And for this deep dive, we're going to explore exactly what this incredible technology is, how it works, its unique magic, its immense advantages, which are truly reshaping heavy industries, and, maybe surprisingly, the range of sectors that rely on it daily.
So our mission for you, the listener.
Yeah, our mission is to offer a shortcut, really. A way to understand this niche, yet absolutely critical engineering solution that quite literally keeps our world moving. You'll grasp how precision meets practicality in some of the heaviest industries out there.
Okay, let's unpack this then. Our source material gives a perfect real-world example. A call comes in from a power plant, right? Chemical corrosion had basically chewed up a critical bearing housing surface.
That's the part holding the support bearings for the rotor. Crucial.
Absolutely critical. And the core challenge here isn't just like one damaged spot. A turbine rotor is supported by multiple bearings, and their center lines have to form a perfectly straight line, perfectly collinear.
Otherwise, it just won't spin smoothly.
Or safely.
Exactly. For that rotor to spin smoothly, efficiently, if even one bearing is slightly out of alignment, the whole system is compromised. And like we said, taking that massive casing to a workshop.
Weeks, maybe months of downtime. Crippling.
So the big question was, what kind of revolutionary solution emerged? How did they shift the whole paradigm for these repairs, allowing you to fix something that massive, that precisely, right where it stands?
And the genius here is the immediate answer. It's the fastest way to repair a damaged turbine casing is with on-site portable line boring. Simple as that, conceptually.
Right.
This method lets you remachine damaged bores using other undamaged bores as a reference, so you restore perfect alignment without moving the entire casing.
Oh, okay. Using the good parts as a guide. Precisely. The key insight, what really changed the game, is literally taking the workshop to the turbine. It's a fundamental shift in repair logistics.
Okay, taking the workshop to the turbine. I like that. But you hear the term line boring, and maybe it sounds incredibly complex, almost sci-fi.
It sounds that way, yeah.
But the core idea, once you get it, is actually surprisingly straightforward and incredibly powerful, especially for these urgent on-site repairs. So what does that actually look like? How does a machine that can fix something so huge with such precision, how does that work?
Absolutely. So a portable line boring machine is essentially a specialized transportable tool. It's designed specifically to precisely repair and restore these cylindrical bores in heavy machinery right where it stands.
So it's basically a mobile, high-precision machine shop.
That's a great way to put it, yeah.
Yeah.
As for how it works, well, the process starts by securely mounting a very rigid boring bar. This bar has to pass through the bore or sometimes a whole series of bores that need fixing. Then comes the really critical part. Meticulous alignment. They often use advanced laser tools now to verify the bar's position relative to the original specs, the OEM specifications.
Lasers. Wow, okay, so super precise.
Oh, absolutely. This laser precision is key. It ensures the repaired part is literally as good as new, dimensionally speaking. It prevents future problems, like breakdowns from imperfect alignment later on.
Makes sense.
So once that bar is locked firmly in place, a cutting tool is attached to it. As the bar rotates, this cutting tool is fed along its length, and it precisely shaves away material from the inner surface of the bore.
Just shaving off tiny amounts.
Tiny amounts, but with incredible accuracy. It's remarkable how accurate this process can be. We're talking tolerances as tight as a fraction of a thousandth of an inch.
A fraction of a thousand, that's tiny.
It is. And that level of precision isn't just impressive, it's absolutely critical. It prevents issues like vibrations or steam leaks in high-performance machinery. It ensures, for example, that a multi-million-dollar turbine spins with basically zero vibration.
Right, which is essential for its lifespan and efficiency.
Exactly. And there's another layer to this. If a bore is really badly worn, excessively worn, many modern line boring machines also have an automated welding system built in.
Welding, too, okay.
Yeah. So new material is added, first using this welder, building up the damaged area. Once it's built up, then the line boring process machines it back down to its original design dimensions.
Ah, so it's a two-step repair sometimes. Build up, then machine down.
Precisely. That build-up and then precise machining, it's fundamental to true on-site restoration when there's significant wear.
Okay, that makes sense. So heavy equipment breaks down, that's just, a fact of industrial life.
It happens.
But the real nightmare, as we touched on, is the sheer logistics. Transporting something enormous to a workshop, it's just a colossal undertaking.
Huge costs, huge delays.
But this portable approach, there's a much, much better way. It's genuinely fascinating how bringing this precise repair capability directly to the machinery completely transforms things. What are the truly game-changing benefits we're talking about here?
Well, yeah, the sheer efficiency you get from this on-site capability,
Right.
it leads us right into the advantages, and they are significant.
I bet.
The main ones are drastically reduced downtime, massive cost savings because you avoid transport and disassembly, and you maintain incredibly high precision. Plus, it allows repairs in really remote locations, getting critical machinery back online faster than ever before.
Okay, let's break those down because they sound huge. Drastically reduced downtime.
Yeah, this is arguably the single biggest advantage. Think about it. The traditional process: dismantle, transport, wait for the workshop slot, repair, transport back, reassemble.
Weeks, months.
Easily. Weeks or even months. With portable line boring, the repair happens in situ. Right there.
On the spot.
On the spot. This cuts a timeline of weeks down to just days, or sometimes even hours. That's often the difference between a company weathering a crisis and, well, not.
So it's not just a repair, it's like business continuity insurance.
Exactly. Then you have the significant cost savings. When you cut out the transportation and the complex disassembly-reassembly,
You cut out a huge chunk of the cost.
a massive chunk. No more paying for heavy haulage, specialized crane rentals, those high workshop fees, or all the labor hours for teardown and reassembly. The cost of an on-site repair is often just a fraction of a traditional workshop repair.
And we're not talking small change here.
No, absolutely not. We're talking about potentially preventing losses in the hundreds, thousands, even millions on a single major breakdown. That makes a real difference at the bottom line.
Wow. Okay, what about precision? You mentioned that too.
Right? High precision where it counts. And interestingly, doing the repair on-site often results in a more accurate outcome, especially for machinery with multiple collinear bores, like that turbine example.
More accurate on-site. How?
Because you're using the machine's own undamaged bores as reference points. That ensures perfect alignment relative to the machine itself. You're machining the component relative to its own true center line, which can actually be more accurate than trying to perfectly recreate that alignment in a separate workshop environment.
Huh. That's counterintuitive, but it makes perfect sense when you explain it.
It does, yeah. And finally, there's quick setup and versatility. These machines are designed for rapid response. An experienced operator can often get one set up in well under an hour.
Under an hour.
Often, yes. And their modular design means they can be configured to work in tight, awkward spaces where, other tools simply couldn't fit. I remember one job, a remote mining site, middle of nowhere. Bulldozer was completely dead in its tracks.
Nightmare scenario for them.
Total nightmare. Without portable line boring, that machine would probably have needed an airlift out. Huge cost. Instead, we were in, repaired, and out in a day.
That's incredible. It almost sounds too good to be true. We've heard about the precision, the versatility, but how challenging is it really? Achieving that level of accuracy in what could be a dusty, noisy, or remote industrial environment compared to a clean, controlled workshop. Are there trade-offs? Or maybe situations where this on-site approach isn't the best fit?
That's a really good question.
Yeah.
And it definitely speaks to the expertise needed. It is certainly more challenging than a climate-controlled workshop, no doubt about it.
Right.
And that's precisely why the skill of the operator and the sophistication of the equipment, especially those laser alignment tools we talked about, are so critical. The operator has to know how to shield the work area, manage vibrations, account for temperature changes maybe.
So it's not just the machine, it's the person running it.
Absolutely. The trade-off, though, it's often minor compared to the sheer economic and logistical benefits of doing it on-site. The situations where it might not be the best fit, usually only if it's a relatively small component, something easily removable and transportable. For anything significant, anything large or deeply integrated into a bigger system, on-site is almost always the clear winner.
Got it. So, okay, we know it's versatile, but scale must matter, right? When you're thinking about the actual job, not all boring jobs are the same size.
Definitely not.
You wouldn't use a massive machine designed for a huge turbine casing to fix, say, a small engine part needing fine precision, would you?
Absolutely not. And conversely, a small machine just doesn't have the power or rigidity for a massive construction frame or something.
So can you explain the clear distinctions, the different types of machines based on the job?
Yeah, there's a very clear distinction. You basically have large line boring machines and small line boring machines. The large ones tackle those enormous, heavy-duty on-site jobs like the turbine casings we discussed, or huge components on ships.
Heavy.
Exactly, the heavy hitters. Small machines, on the other hand, they're tailored for high-precision work on smaller parts. Things like engine bearing pockets, gearbox housings, where finesse is key. The difference is really stark, both in capability and application, based entirely on the job scale and the precision needed.
Okay, tell us more about the large ones first, the heavy hitters.
Right. Large line boring machines, they're built for components with really big diameters, sometimes up to 80 inches or even more.
80 inches, that's huge.
It is. Now, their modular design still often allows setup, even in relatively confined spaces, which is impressive. But their real strength is their high torque and power. They need that to make deep, aggressive cuts, if necessary, on these massive workpieces.
What are typical jobs for them?
Typical applications include repairing those steam and hydro turbine casings, machining marine stern tubes, that's the passageway for propeller shaft through the hull,
Right.
aligning large coupling holes, reboring the bed plates for massive diesel engines like in ships or power generation.
Yeah.
The really big stuff.
Okay, so what about the small line boring machines then? Precision and flexibility.
Exactly. Small line boring machines are built for precision and flexibility. Their boring diameters start much smaller, maybe around 1.5 inches, sometimes even less.
Tiny compared to 80 inches.
Worlds apart. They are much lighter weight, obviously, and they're ideal for finer operations. The goal here is achieving a perfect surface finish and incredibly tight tolerances on smaller components.
In their applications.
Typically things like repairing engine bearing pockets, very precise work, reboring valve bodies, general maintenance on smaller machinery components like gearbox housings, hinge pins on equipment, A-frame supports, that kind of thing.
So while they both do line boring, their worlds are quite different depending on the job.
Dramatically different.
Yeah.
It's all about matching the right tool, the right scale, the right power, and the right precision capability to the specific task at hand.
It's genuinely fascinating how widely applicable this tech seems to be across those different scales. You might initially think, okay, massive machines, incredible precision. Maybe this is just for power plants or these gargantuan ships.
That's a common first thought, yeah.
But really, you'd be surprised how many essential heavy industries are relying on this critical repair capability, often completely behind the scenes without us ever knowing. So, beyond power generation, who else is out there? Which other common users are quietly depending on line boring to keep things running?
Oh, you're absolutely right. Its reach is much, much broader than you'd initially expect. Besides power generation, line boring is absolutely crucial in construction and mining, think heavy equipment repair.
Mm-hmm.
In automotive, especially for larger engine manufacturing or repair, marine and shipbuilding, obviously, for critical propulsion systems, and definitely in oil and gas for maintaining vital rig infrastructure and refinery equipment.
Okay, can we get specific, like what kind of repairs in each?
Sure. Let's quickly run through some examples. In power generation, as we've discussed, it's repairing turbine casings, nozzle chambers. Those direct the steam or gas flow.
Critical for efficiency.
Absolutely. And other key components in steam, gas, and hydro plants. For marine and shipbuilding, especially dealing with that harsh saltwater environment, it's vital. Machining stern tubes, rudder, pintles the pivot points for the rudder.
Okay.
Drive shaft housings, A-frame supports,
Yeah.
or for building new ships and for repairing vessels already in service.
Right. And heavy equipment, construction, mining.
Huge users. Think about excavators, bulldozers, big mining trucks. Line boring is used right there on site to repair worn bucket pins, hydraulic cylinder mounts, articulation
For
points.
joints where things pivot and move.
Exactly. Those pivot joints that take immense stress. Fixing them quickly keeps those expensive machines working and projects on schedule.
Makes sense. Automotive. You mentioned larger engines.
Yeah, mostly for larger engines you'd find in industrial or marine applications, maybe heavy trucks. It's used for precision repairs on engine blocks, bearing housings again where alignment is critical. And oil and gas must be vital there with the cost of downtime. Catastrophic downtime costs there, yes. So line boring is critical for on-site repairs, often on offshore rigs or in refineries, specifically for large components again, like turbine casings, large pump housings, engine bed plates, keeping that energy infrastructure running.
But just general manufacturing.
Yep, general manufacturing too.
Sure.
Precision machining of various industrial components, maybe large gearboxes, press frames, drive shaft housings for factory equipment, ensuring high-quality production and maintenance across the board.
Wow.
It really shows how this ability to perform precise on-site repairs makes line boring just an indispensable tool across a really wide range of sectors. It's one of those hidden technologies keeping the entire global industrial machine oiled and running.
So to bring it all back then, when we think about that initial image, that crippled turbine costing millions an hour, it's crystal clear. On-site portable line boring does exactly what it says on the tin. It brings precision repair capability directly to the heavy machinery.
Right where it's needed.
And this crucial capability isn't just, convenient. It's the direct antidote to those industrial nightmares. It drastically reduces downtime, saves absolutely enormous amounts of time and money across so many essential industries. It really is an aha moment when you realize how such a specific, maybe even obscure-sounding tool can have such a massive impact on the world around us.
And that's the truly fascinating part, isn't it?
Yeah.
This specific example, line boring, it really highlights a much broader idea. It shows how these highly specialized, incredibly precise engineering solutions often operating completely out of public view.
Totally invisible to most of us.
Exactly. How they are absolutely vital for maintaining the complex infrastructure, the heavy machinery that really underpins our entire modern world. That kind of encouraged us, maybe you listening, to consider how many other invisible technologies like this are quietly humming away, keeping our essential industries running smoothly.
Yeah.
It hints at these, endless depths of knowledge and innovation just waiting to be explored, often right beneath the surface of our everyday lives. So much intricate engineering making everything possible.